Okay, so here we go. We're on 4.4, the last section that's new for us. So good job, guys. Made it to the end. And there are just two types of questions we're mainly focusing on today. We're actually not learning any new math, really. We're just learning how to apply the exponential and log functions to solve like word problems. So application questions. Two things to know: how to solve exponential growth decay problems and then amortization problems. So first, exponential growth decay problems. For these types, we just use this formula. A is equal to A naught times e to the kt. Here, A is the end result after growth or decay. A naught, when we put the subscript 0, that usually means it's like the starting position. So the original value at time 0. So A naught is the starting value. K is the growth rate. And T is time. If you look at it, it's kind of intuitive, right? This is like some starting value times whatever your E is like the base, so it's going to grow exponentially, time raised to the power that you're the power that you're raising it to is the growth rate times the time. So like the exponent is basically like, kind of think of this as being like the sort of independent variable kind of. Now let me show you a picture of what that's going to look like. So here it's going to write A is equal to A naught e to the RT. Okay, T, I say. I say R because sometimes you use R for rate. Okay, and then time is going to be, I'm just going to leave time as the axis. So as time progresses, this is the growth. So you'll see, okay, let's just start with A not equal to 1. So this is your starting value. Yeah, starting value at 1. What happens as time progresses? So if the rate is 0, then you see there's no change, right? It's just a straight flat line, like we would expect. If the rate of change is 0, then it's not changing. So it stays at 1 as time progresses. If the rate is positive, so 0.1, you see it has that same shape, kind of like how we saw with the compound interest, right? Because it's also an exponential function. This is e raised to some power. You have a base raised to exponential power. So it increases kind of like that same shape, right, as a compound interest. It just steepens faster and faster. And then the higher value, the higher the growth rate is, then the steeper that change happens, right? It starts to get real steep. So even at 0.1, it's already pretty radical. 0.2, 0.3, 0.4, 0.5. Here's at 1. And then it's doubling super fast, right? This is 40 already at about 4, you're already over 40. Actually, 50, over 50 at 4. Time 4. If your growth rate is k is equal to 1. So growth rate of like k equal to 0.1, that's already pretty fast. Like you're at time 30, you're already at about over 20. Okay, now this also applies for decay. So if your k value is a negative value, then what that means is instead of growing, you're going to be shrinking. And it's shrinking towards 0. But let's start with the higher value because it's kind of hard to see what's really happening when you're growing if I start at 0. So let's start at 1,000. I'm just going to zoom out so we can see. Let's do 1,005. Okay, so here you see that red line on the top. Okay. There's that red line on the top. This is where we're starting now this time. Okay, 0. If I go negative 0.1, see, so starting position at 1,000, right? And then as time progresses, it gets smaller and smaller and smaller. And then it just approaches 0. E to the negative power means it's like 1 over e to something. So it's not going to turn negative, but it's going to go, the denominator is getting bigger and bigger. So it's getting it closer and closer to 0. Yeah. So this is the model they use for exponential decay. Let's kind of fine tune this a little bit. Let's say to negative 0.1. So get it. and negative 0.037, for example. Here, you can kind of get a better picture of what's happening. A lot of times when we talk about in like when they use carbon dating, is they talk about half-life, and that's just how long it takes for the thing to get halved. So like if you're starting at 1,000, how long did it take you to reach 500 here? And then how long from there does it take you to reach 250? And that half-life is going to be the same time period each time. So if you look here, it took you about 18.6 time intervals. So maybe it's years or something, or millions of years, whatever, hundreds of years. 18.6 to reach half, or close to 19, right? And then to reach another half at 250, that should take you another 18 years. So another 18 years would be about, or close to 19 years, right? Another 19 years would be close to 38. So let's see, about 38, we should hit our second half. Yeah, about almost 38. And so we're second half at 250. Yeah. So this is the idea with exponential decay. So again, if it's negative, then it's going to be decaying, and then if it's 0, it's flat, and then as k goes to positive value, then we start to grow exponentially instead. So here, you can kind of fool around with it. See, it's a picture: flat, growing, and then shrinking. It's negative. Does that make sense to you guys? You guys kind of get a picture of what's happening?
Mm-hmm.
Okay, so that's just the formula we're using here. This is for growth and decay problems where your function is growing exponentially. This can be used to model, like, for example, virus spreads, or like I don't know. It's only one type of model, and like if you're talking about something like a virus, probably is not going to stay exponential because it's going to have limitations that are going to prevent it from doing that. But it will maybe be exponential for some period of time. All right, anyways, let's take a look at the first types of questions then. Oh, let me make a comment about what it says here first though. So when we solve equations like this, what we typically do, and this is true for anytime you're solving equations, you're gonna just input the values that you know, numbers that you know, and solve for what is left over. And now when you're doing these exponential decay and growth problems, what usually happens is you don't know k, you don't know the growth rate. No, that's not always true, but it's kind of a common thing where you have to solve for k. And then after you solve for k, then you kind of have to answer a follow-up question where you input something else to solve for t, or solve for a naught, or solve for a, something else. Okay, you'll see what I mean in the first couple of questions. So let's try the first two. First one says, number one, 30 days ago, there were 10 confirmed. This is just made up, by the way, and don't get too alarmed because the growth rate is not exponential like this, but I just kind of made stuff up. It's not going to be this radically exponential, I don't think. Anyways, 30 days ago, there were 10 confirmed cases of COVID-19 Hawaii. Today, there are 600 cases. If the case continues to grow, if case grow exponentially and were to continue growing exponentially, sorry, this is not supposed to be there. How many cases would there be in 30 more days? All right, so I'm gonna actually stop this video and come back to the whiteboard. So stop and see if you guys can figure